Hey, what's going on?
Okay, let's get started. So, looking over the homework 4, and so it's done. There's some replays are posted, and there are comments. There are a few things though that I'd like to point out that came up several times. So, maybe you have formats for your work that is like super clear and it's all very nicely and can follow it, but it's somewhat variable with other folks. Okay, so remember, you need to communicate to me what you've done, and the reason for that is because soon you'll be out there making calculations like this for somebody who's paying you, and you want the calculations to be verifiable by, well, you want it to be correct, first of all, and they're going to be more likely to be correct if you can read them and verify that they're right. And then somebody else also will need to verify them in many cases. So keep that in mind. There might just be some, things you can do for clarity. Some people feel like paper is really valuable, so everything is like crammed into really small space. You could give your calculations a little bit of room to breathe, make it easy to read. Many of you, I put comments related to try the one fraction format. And here's an example. This is from one of the problems, 3.8, I think. To calculate the permeability, there's the formula. So here's one way of doing it. So if you look at that, what are the units that result from that calculation? I mean, you can figure it out, but you got to go, and this centimeter cancels with that one. This one gives you a second squared. So up here it's what? Grams per second squared. Then you got to go here, figure out what this is, and then figure out how they all cancel. I mean, you can do it and get it right, and many of you did. But if you use one fraction, this is the one fraction format. Instead of doing it like this, put the seconds down here, and instead of doing it like this, put the grams and the centimeter cubes up here. Then with one fraction, it just cancels. The 2 seconds cancel here. The grams and the grams. We got a centimeter, the centimeter, the centimeter squared. So this works out more reliably. Not to say this doesn't work, for sure it does. But there's just fewer chances of there being a mistake. The units here end up being a super good check on whether you've made a mistake. Doesn't say, if the units work out, it doesn't say that the problem's right, but it sure says that it's not wrong. If you miss a term, then the units don't work out to be right, and problem that is like an immediate check that there's a problem. So always include the units. A lot of people were just like writing numbers here without including the units. Takes a little more space, but it gives you the opportunity to check and see whether you've missed something. Okay. So this was problem number through 12, I forget, it was some kind of volume, you're calculating volume of water from water table rising or falling, something like that. So this was one of the answers. So in order to do that calculation, here was the calculation. These are the numbers that okay, so it was that and that, 20 meters thick and head drop of 3.4. Okay, so remember, I'm sure everybody did, like in high school or junior high school, significant figures, right? So how many significant figures do we have here? 2. So if you multiply numbers together, can you like create more significant figures? You're going to be limited by when you multiply numbers together, you're going to be limited by the least number of significant figures. So here, we only know the water level change to the nearest tenth of a meter. Okay, over this big area here. So it could be like this, or it could be like that. But then, if this is the answer you give, this is cubic meters, that's 1 liter. So you have, I mean, this is like a bunch of Olympic-sized swimming pools, and you're giving me the answer to the nearest liter. So I don't know. I think what people think is that when they give results like this to a whole bunch of significant figures, that it's like more accurate or something like that. And I mean, it has more significant figures, but there's no way you could know this. And if you just think about it, I mean, you're doing a calculation where, you know, the water level is like here or here, somewhere in here, and you're telling me that you know it to the nearest liter. I mean, come on. That's just impossible. So I'm not going to be a big enforcer of significant figures, but just keep in mind when you say something like this, it's impossible to do it because you really are starting with just 2 significant figures, and I don't know, just gives kind of an unreasonable impression about the result. Okay. All right. So let's see. A couple other comments. There were a variety of small mistakes. Most folks got everything in good shape. I think probably the one where the most points were missed was, I think, number 3 on the handout, where you had to use the specific yield. And in order to get the specific yield, you had to calculate it from the porosity of the specific retention. So it wasn't given. So, and you had to do it, you had to know that the specific yield plus the specific retention is equal to the porosity. So if you're not given the specific yield, you were given the porosity and the specific retention, so you could calculate that. Okay. I'm given some supplement comments on the contouring in homework 3. William, the grad student, has gone through and graded them, and he sets up, you know, kind of a standard for the grading, and I'm not changing that, so the grades will stand. But he was being a little bit generous, I think, on some of the contouring. So I'm going to go through and give you some comments on, particularly on the one in the book, because there are a variety of little details on that one that you should know about. So there's also the posted the key of what that one looks like. So you can check that out. But for some of you, you might notice some comments coming in on that homework. So those are just to kind of point out some things for future reference. Okay. So there's also the key for homework 4 is posted. All right, any questions? Okay, so want to get back to the problem where we were at the end of class last week, or last class, where we've got the we have an equation for all of the interior points. So that's done. The exterior points, these also need equations where we have constant head boundary. That's easy. We just have a simple equation where we can specify what the hydraulic head is. But for no flow conditions, we can't specify what the head is per se, so we need a different strategy. So what I'm going to do is say, okay, we've got no flow conditions here along this boundary, and then these are instead of indices, I just use these letters, so it'd be easier to refer to them. So the equation that we had was, I think it was, the H at B was the order times the sum of the heads all around it, right? H E plus H A H E H C plus what R over K R of delta X squared, I won't get that, over K B R at A. I think that's right. Does it look good from your notes? From the end of class last time? Everybody have notes from the end of class? Check that.
Would it be RB?
R. Yeah, right. Yep, it's R. We're doing it on that one. So the new charge at B. Yeah, good, thanks. Okay, so this is the form of the equation that applies everywhere. So it would apply here. But if it's a no flow boundary, then we don't know what that is, what that one is, right? Because this is outside of the domain. So we don't know what that head is. But if it's no flow at let's see, Q X at B is 0. So the flux in this direction is 0. Right? So that's going to be minus K dH dx. Right? Well, K can't be 0. So it must mean that this is 0. If we write that in finite difference form as a centered first derivative, then that would be HC minus HA over 2, let's call it 2 delta X. So this would be delta X. Okay. Well, and okay, we can include this too. So we have minus K. All right, so if the flux is going to be 0, the only way really to do that in a reliable way is if HC equals HA. And then the gradient is 0 and the flux would be 0. Okay, see how that works? If that's true, that's 0. So at this point, HC equals HA. So we could just do that. Or, we've got two of them, so we could just get rid of that and put a 2 in there. Okay, so that gives us now an equation at the boundary for any boundary point that's on a no flow boundary. Okay, so we're good. We've now got all of those points. So we have same number of equations as unknowns, and that we can solve. So I think I have one more slide here. Yeah, okay, so here's one more case. So what if we have a well? So if you have a well, then we're pumping water out. And the way to handle that is to say that we're pumping water out at a point. But conceptually, what's happening is that inside that grid block, we don't really see any details. We're just assuming that the head inside that grid block can be represented by the head at that point. And we're kind of averaging out all of the variation inside of that block. So if R is a flux, the recharge flux, and for pumping water out, you can think of that as a negative recharge. And if Q is a flow rate, then we can turn it into a flux if I average over this block by just taking Q and dividing by the area of the block. Okay, so Q is going to be negative the recharge times the area of the block. All right, or the recharge is the pumping rate normalized to the area of the block, change the sign. All right, so then we go back here. This is the recharge. So if we have a pumping well in that block, we just take care of it here by modifying the recharge term. Great. So that allows us then to have an equation at each cell. And everywhere we have unknown, we can have recharge. We can have a pumping well or injection well. And it gives us a lot of flexibility. Okay, so this will be the basis for the numerical modeling of hydraulic heads and aquifers, and then also flow. Okay, so here's what we're doing. We want to set up a groundwater model. We discretize the governing equation and boundary conditions. We have the same number of equations and unknowns. We need to solve that system of simultaneous equations. We get the hydraulic head at all these points. We use finite differences to get the gradient in the hydraulic head multiplied by K, flip the sign, that gives us the flux. If we have the flux and we divide it by the effective porosity, we get the velocity everywhere. And once we have the velocity, we can put a point in there and integrate the velocity and get how the point moves through space. So we can determine the flow through the aquifer. Okay, so we got to solve to get the hydraulic heads. Turns out it certainly is doable, but there's a lot to it. If you have many equations and many unknowns, then that ends up being a big numerical problem. And there's been a lot of work done on how to do that, particularly for this kind of problem. And groundwater modeling codes, one of the main things that they do is solve that problem of many simultaneous equations. ModFlow is the de facto standard for groundwater modeling in this country. It was developed by the USGS back in the 80s, really, 1980s. Yeah, this is the first publication. And it still is widely used today. What ModFlow does, ModFlow is here by the USGS, and it stands for Modular 3D Finite Difference Groundwater Model. What it does is it calculates the hydraulic heads and the fluxes. Written in Fortran, and it solves these partial differential equations that have been written in finite difference form. There are a variety of modules, and modular, for doing various different things. There are also a variety of different solvers. In 1983, when they first started doing it, they came up with a couple of the solvers that were the most popular at that time. But since then, there's been a lot of work done on how to solve these problems, and there are now solvers that are faster and more efficient. So a variety of solvers that are included in this. Okay, so I'm going to use ModFlow. It was done in '83. There have been a bunch of revisions, updates in 1988, 2000, and so on. These are fixed problems, just regular software updates. The original way that this was implemented is as a batch file. So it ran with the DOS command line. Who knows what a DOS command line is? And no? Okay. So it used to be that for Windows, that when you were using a computer, you had just a single line. You would type in a command and run things that you wanted. So this is the original way that computers, the original operating system for computers. You set up a file that has a bunch of numbers in it in a certain format, and you run the code, and it reads that file in and does the calculations and spits out another file. So efficient, but clunky and cumbersome and pretty frustrating to use. So this is the way it was for a long time. But in more recent years, there have been software that has come along with graphical user interfaces to make life a lot easier. The one we'll use in class is called GMS, the Groundwater Modeling System. There are some other ones. Groundwater Vistas is another commercial one. Model Muse is open source. And these all have graphical interfaces where things look good and you can use your mouse. So this is the standard for aquifer simulations in the US. If you're doing modeling for the consulting world, this will almost certainly be one of the ones that you're using, at least to some extent. There are some other good codes out there, but this has been around for so long and used so much that it is standard. Okay, so ModFlow has a big manual, and here's a page from the manual. Here's the grid, the finite difference grid, some layers, and there's a drain. And this is what the input looks like. So a bunch of numbers in a format here. This is this is maybe the size of the grid here. Each one of these is one of the grid blocks for one of the layers. And these numbers are some code about what the boundary, something like that. You'd also have grids like this that have the hydraulic connectivity. And then other stuff here that various information about how the model should be set up. So when this code first was developed, in order to use it, you had to go in here, and this is some code del C, and so you have to know what del T was and type the number in there, and so on. And it goes on and on. Okay, so that's how you did it. It was tedious. Here's some more of this good stuff. So that's the way that is set up. Then there's another package that'll be important called modpath. And modpath does particle tracking to produce flow paths. So the way that it works is that you run modflow, it calculates hydraulic heads and does the gradients and determines what the fluxes are and what the velocities are. And then modpath goes and traces particles through that flow field. And it shows you what the flow path is. So these two codes work together. You have to run modflow first and then run modpath. Okay. So they're trusted, but they're tedious. So groundwater modeling system, it is a graphical user interface. So the people that develop this, they develop the package that has nice screens, that has windows on there. You fill in the numbers in windows instead of putting it in a formatted text block. It's got a convenient way to set up the geometry of the problem. And then what it does is it takes all of that info that you put in, and it writes that input file in the format that Fortran is looking for. And then it executes modflow and modpath. Modflow and modpath then generate output, and it reads that output and puts it in a nice, pretty format. Okay, so it's not really doing the calculations. Modflow and modpath are doing that, but it's making it easier to use these codes. Okay, so we're going to use this code in class, GMS, and it's available in Brackett Hall. On the 4th floor, we have a departmental computer lab. So it's installed on the computers there. It's also, we have a site license, and you can install it and run it on your computer, so long as you have a PC. If you have a Mac, I don't know, maybe, but no guarantee about Mac. If you have a Mac and you can set up a Windows emulator, that's going to be your best bet. If a native Mac, I doubt it. Okay, so if you can't get it, if you have a Mac so basically, we're not guaranteeing that you can use this code on your computer. You'll have access to it in Brackett Hall. If you have a PC, then probably a high chance that you can get it running on your laptop. So you need to go and get access to the site license, and we got a page on Canvas for doing that. So go and check that out and see how that works. Let me know if there are problems. So the first thing that we're going to do is get going with GMS, and then we're going to run the FlowNet problems. there's several of you that said when we were doing this, why don't we just use a model? And in fact, we're gonna. That'll be the first step. I had you do the flow nets by hand to kind of train your intuition and train your perspective on what these things should look like, what these flow fields should look like. So I really think that drawing it out by hand and trying to get it right helps with that. But we also want to, well, we can also show you how it works for real. Here's one of the flow nets, right? This will prove it to you that even though it may have seemed impossible to get it all to work out right with everything perpendicular and the right ratio, here it is. So we'll do these problems first, and then we'll move on to more realistic problems. And the way that we'll do this is there'll be some videos that go through step by step on how to set these problems up. I used to do it in class, go through it, but it's like really boring, and you really need to have like the step by step as you're doing it. So the video works really well. The way this is going to be set up is that there'll be a Project Explorer over here, where you'll have kind of the major components of the setup of the model. There'll be graphics here, where you can see the head contours and the streamlines. These head contours came from ModFlow, and then ModPath generated these flow paths. So over here, you're going to have what's called 3D grid data, and that has the computations and results. You're going to have map data, which has the problem specs, geometry, properties, and then image data about the layout of what this thing looks like. So here's some more detail. This is like one of the problems where we have flow under a dam. You can see the grid there. There's a finite difference grid on that. And then here's the hydraulic heads, and put in some flow paths. Get that result. Okay, so yeah, there it is. So there's an upcoming assignment for this, and this will give you a chance to get going with the GMS package. Okay, so check that out, and if you have problems, let me know. One of the big reasons why we want to do one of the big reasons why we want to have numerical models like that is that we want to be able to set up models in 3D and include geologic features that are realistic. We want to then have our model mimic reality. Okay, so we want to know the flow paths are going like this and like that. If we have if we're interested in this place, is the flow going down, and what direction is it heading, and where does it end up? So we want to be able to mimic reality, and in order to do that, we have to have the aspects of the geology included in the model. So we want to learn about what the geology is like around here, and this will be the hydrogeology of the Piedmont. And what will be important is what the different hydrogeologic units are, how they got there, what their properties are, and what their geometry is, and what that flow system looks like. So here's a map of the hydrogeology of the Southeast. So we're here. And this kind of light purple area is the Piedmont physiographic province. And this area is underlain by crystalline rock. And there's some other things here, but for the most part, it's crystalline rock. As we go down towards the coast, we get into the coastal plain sediments. So right here, Columbia is right here. It's right on the boundary between the Piedmont and the coastal plain. And this band right here is created with what's called clastic sediments. So sediments that are formed from sand, silt, and clays. And then here, this is the Floridan limestone. So this is carbonate. And it forms a big aquifer in Florida, but also coming up here in a little bit into South Carolina. So the crystalline rock here in the Piedmont, the conceptual model includes what geologic materials are here. And we'll see that there are these three main geologic materials, what the flow system is like. It's a local flow system, and the typical properties of the Piedmont. So here's a cross section through North Carolina. So we're I think around here someplace, and this is representative of what things are like through South Carolina as well. So we're in the inner Piedmont, so we're like right in here, and you can see this cross section. These are the Piedmont rocks, and then they slope down, and then these are the sediments from the coastal plain on top of them. And then back here, back less is the mountains. The mountain you can see from from certain places on campus. So fractured crystalline rock, that's what underlies this area. And this is what it looks like. So the simplest version is here. This is a picture from a granite quarry in Elberton, about an hour from here. So this is very uniform granite and really low porosity, and there would be very little groundwater flow through this material, but it has a crack in it. That's a crack, and you don't see much of the crack here, but you can see it's open here by about 1 millimeter or so. So the water can get transmitted through things like this and cause and sustain flow. So this is like a simple fracture. Fractures consist of these things, kind of a zone of these things that are grouped together and that can coalesce. And here's an example of a fracture zone, horizontal fracture zone about this thick. And we can see the rocks all broken up in here. And then there's also a vertical fracture, several vertical fractures coming up like this. Okay, so this is important because we see here that we can have fracture zones that are much thicker and more transmissive than this one would be. We also see, though, this thing has got pretty good lateral extent. So we can have flow like this, horizontal flow through this fracture. But there's also these vertical fractures. So that's important because in order for there to be flow, we have to have these fractures connected to other fractures and forming a connected network. So here's an example where you have a horizontal and a vertical fracture. And those are the two components that you need to have a network. So here's a picture from a quarry, and you see a lot of fractures here. Cracks out all through this face. Many of these fractures that you see here are from explosives that they use for this quarrying process, where they blast and they take the rock out and use it for, this quarry would be using this rock for like gravel for roads. But you can see this fracture right here. This is this surface right here. It comes in, and that's kind of the fracture right there. I don't know if you can see that. So this is water right here, and this is water. So this fracture here is transmitting water, and water's flowing through it, getting recharged up here at the top and flowing out and coming out here. So there's flow through these fractures, and in fact, to the extent that we have groundwater flow in this area, it's through these fractures. All right, so hydrogeologic units. These are the geologic units that are important to the groundwater flows. And in the Piedmont, we have generally recognized at least three main hydrogeologic units. This is a plug, goes down through the earth. Here's the ground surface, there's a stream. And what's shown here is crystalline rock with this kind of structure here. The rock that I showed you on the previous page, I'll take a quick look here. So this is granite. This is igneous rock. This is crystalline rock, but it's a metamorphic rock called gneiss. Not NICE, it's spelled GMEISS. It's banded. It's difficult to see the banding here, but this is probably the most common rock type around here, the high-grade metamorphic rock. This is also the same high-grade metamorphic rock. Crystalline rock, so the crystals have grown together and are interlocking, and very small pore spaces between them. So this is the crystalline rock with fractures. And you can see there, that's a horizontal fracture called a sheet joint here. And then here's some vertical fracture. But what happens is that the crystalline rock that we have here, the gneisses, have minerals that are unstable at shallow depths, and they weather out, and they chemically altered to clays. So up here at shallow depths, this rock has been weathered, and the weathered material is called saprolite. That's a rock that has been pervasively altered by weather. I'll show you an example here in a second. And then this is the fractured metamorphic and igneous rock that I showed you on the previous slide. And these two, this weathering process causes big changes in the crystalline rock and metamorphic and igneous rock. So there's also recognized the transition zone between these two. So these are the three main hydrogeologic units in the Piedmont. So there are really two styles of how these different units are arranged. So where the area is underlain by banded or layered metamorphic rock, gneisses, that's how you spell gneiss, or another type of metamorphic rock called schist, where you have those materials in the subsurface, then there's a fairly narrow transition zone shown here. So it goes from intact rock to the saprolite over a fairly narrow zone. Where it's granite, that other rock that I showed you on a couple slides ago, then the transition is over a much broader area. You've got fractures and the saprolite up here. So a key thing in both of those cases, though, is this material called saprolite. So this is a picture of saprolite here. This is on Route 23. Once you cross the lake and go up the hill, there's a grocery store on the right. I think it's a Food Line now. I think so. There. Yeah, it used to be, when it first was built as a balloon. But the Food Line, before that was built, there was a little hill there, and it looked like this. So you can see some patterns in here. And what's going on is that the metamorphic rock, these gneisses, are layered, and they have folds in them like that. Here's some other folds. So these rocks are highly deformed. And when they're at depth, when they're fresh, they're extremely strong. So if you hit one of these rocks with a hammer, then it would potentially just bounce off. But this stuff here, if you see, so see like right in here, see that this layering is that. There's layering that goes down like that. Okay, so the layering that you see here is this same layering. But here, we just took this, in fact, she did most of the work, just took a shovel and shoveled off this thing, this area here, so we could expose all this structure. It just is like, essentially like sand, has very, very low strength. Okay? So it's much different than this in strength, but it still has the same fabric. It still looks the same as this, but a much different strength. So the way that works is if you start with a crystalline rock, this is granite, but metamorphic rocks are going to be similar in that they have crystals that are interlocking. And this rock has three main minerals: feldspar, biotite, and quartz. So in this rock, the feldspars are this kind of pinkish color here. The quartz is clear, so in a rock, it looks gray. So all this stuff in here, this gray, is quartz. And then biotite is black. Okay, so this rock was formed many kilometers deep, and these crystals are interlocking. Feldspar is vulnerable to weathering. It weathers to clay when it gets exposed to water and low pressures and temperatures. Quartz doesn't really do anything. It's stable. The biotite, it also weathers to clay, and the black color there in biotite is because biotite contains iron. And when iron reacts with oxygen, it creates iron oxide, which is red. So what happens when you have rock like this is here's a schematic, and you see that change? See that fantastic graphic? Watch it change. This is the weathering process. Okay, so what happens is the feldspar goes to clay, the biotite goes to clay and iron oxide, and the quartz doesn't do anything. So here you have a strong rock that is, a hammer would bounce off. Now that and that is clay. These are still resistant, but the clay has very low strength. So if you take a shovel through this, just cuts right through here like that, and has very low strength. But we haven't changed the fabric at all, so any kind of layers that we have in there would still be preserved. We've also changed the color. The biotite weathers to iron oxide, so it turns red. So, you know, if you see cuts around here, you see the Georgia red clay, right? The Georgia red clay, the clay is coming from the feldspar and the biotite, and the red is coming from the iron oxide and the biotite. Okay, so the red clay that you usually see in soils, that's been disturbed by plants and animals at shallow depth that form the soils. You get underneath that, and you'll have saprolite that has the fabric retained from the original parent rock. Okay, so saprolite will form an important hydrogeologic unit in the Piedmont, and we'll pick it up next time and see more about hydrogeologic units.